All right, the last hypothesis test that we're going to learn, and it's a new one, it is the chi-squared test of independence, also known as contingency table analysis. This is a test to determine if there is a statistical relationship between two variables arranged in a table. Now, two variables have a statistical relationship if knowing something about one variable can help you know something about a second variable. You know, for example, I might say, is there a relationship between gender and a person's preferred product color? Do men prefer different colors than women do of this product? That would be an example of looking for a relationship between two variables. So once again, I've got a production supervisor, and he's measuring the number of defective and good products produced on 3 shifts in the plant. The results are shown below. For the example, the day shift, we produced 455 good parts, 45 defective parts. Evening shift, 267 goods, 33 defective. And night shift, 168 good, 32 defective. And these are simply the totals in my table. This is known as a contingency table. We have one variable up here, the quality of a part, and a variable down here in the shift that it was produced on. Chi-squared test of independence basically always has the same null hypothesis. There is no relationship between the quality of a part and the shift it was produced on. So essentially, there's always going to be no relationship between variable 1 and variable 2 in the table. And the alternative is that there is a relationship. Calculating the degrees of freedom, you take the number of rows in the table minus 1, the number of columns in the table minus 1, times the number of columns. And remember, you don't count total rows and total columns. So if we refer back to our table, we have 3 rows and 2 columns. We don't count total rows and columns. Okay, so this gives us 3 minus 1 is 2, 2 minus 1 is 1, gives us 2 degrees of freedom. So if we have an alpha of 0.05, 2 degrees of freedom, we get 5.991 as the critical chi-square in this test. Finding the expected distribution involves taking this formula is used to compute the expected value in each cell. The row total times column total divided by the grand total. So this cell belongs in a row with a total of 500 and a column with a total of 890 divided by 1,000 gives you 445. If we would do that in every cell, we would get an expected distribution. If there truly was no relationship between the two, that would look like that. Then we would simply bring each paired grouping. This would be the observed, that's the expected, and I have 6 cells here of data. 455 minus 445 is 10, squared is 100, divided by 445 is 0.225. 267 minus 267 is 0, all the way across. So calculating chi-square in this case is 7.150. Since 7.150 was greater than 5.991, I'm going to reject the null and accept the alternative. And my conclusion is that there is a relationship between the quality of the part and the shift that it was produced by. That means, all of these shifts aren't producing the same proportion of defective parts. I might want to investigate further where our production, where our poor production might be coming from. So this is the chi-squared test of independence, or contingency table test. And you're always looking at a variable as part of a table like this.